All right, so I'm going to try a quick example here of Bode Obstacle course to give you guys a little bit more background as to how it works. So let's say I had this. This, for instance, could represent a position-controlled motor, right? So this could be a position-controlled motor transfer function with basically no electrical pole, right? Assuming the electrical pole is completely negligible. All right, so I put that guy in a feedback loop here. Unity feedback, I can always make unity feedback, right? That would just put something out in front right here. And I needed to design a compensator GC of S. Now, here's the specs. The error to a ramp has to be less than 2%. The error for sine inputs less than 10 radians per second has to be less than 10%. Output for sine inputs greater than 250 radians per second is less than 10%. That's my noise filtering spec. In other words, I said I usually have high frequency noise. Well, high frequency noise in this case is apparently noise above 250 radians per second. And I want to make sure that any output out there is less than 10% of the input. All right, I want to make sure that I cross over at about 50 radians per second and phase margin at least 55 degrees. Okay, so where do I begin with these? Well, first of all, let's start with this one, right? So error at low frequencies is approximately 1 over L, right? Because this guy is 1 over 1 plus L. So at low frequencies, if my L is big, which this guy definitely will be, this will approximately become this. So I know that that has to be less than 10%, which means less than 0.1. All right, so that means that L has to be greater than 10. All right, so that second spec told me that L had to be greater than 10 for omega less than 10 radians per second. Okay, now the other spec that I've got, this sets one of my Bode obstacles, right? So I can effectively sketch that now. Okay. 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 Log 10 of omega. So I've got one obstacle that says L has to be greater than 10 for omega less than 10 radians per second. So here is 1 radian per second. Here's 10. Here's 100. Here is 1,000. So since 20 log of 10 is 20 dB, okay, I show that I have a low frequency obstacle here at 20 dB. Okay, that's basically this. Now, this gives me a high frequency obstacle. Okay, what is that? The output for sine waves greater than 250 radians per second has to be less than 10. Well, our output, we said, is this, L of S over 1 plus L of S, right? That's my output from my input. At high frequencies, I said that becomes approximately L of S. So apparently that has to be less than 0.1 for omega greater than 250 rads per second. Okay, so less than, so that means I draw, so less than 0.1 on a log scale, that's negative 20 dB. Okay, so where is 250 radians per second on a log scale? Well, put that on my calculator here. So I have 2.397. So that basically says he's about 40%. He's 39.7% of the way between 100 and 200. So he's right about here. And I have to clear that. Okay. Now at that point, the easiest thing for me to do is to say, all right, let me plot g of s uncompensated on top of this guy. All right, now here's my original g of s, 1 over s times 0.1 s plus 1. So if I do that, I'm going to be falling at 20 dB per decade for a while. Right, and I would cut through right here. Then I'd hit a second pole, and then I'd fall pretty rapidly after that. Minus 40, minus 60. So I would drop to minus 60 here by 100. Okay, so down here I'm at minus 40 dB per decade. Here I'm at minus 20 dB per decade. Okay, so dropping pretty rapidly. Now clearly I'm good with this high frequency obstacle, but not at all good with this low frequency obstacle. Okay, so what do I need to do? Well, clearly I need to get this thing jacked up. Okay, so let's look at this. I've basically reflected two specs. All right, this one, the sine input, give me a low frequency obstacle, and then this output for sine inputs greater than 250 gave me this high frequency obstacle. Let's think about this error in response to a ramp less than 2%. Error in response to a ramp less than 2%. Well, let's think about that for a second. So if I'm talking about steady state error, okay, I'm saying steady state error for a ramp needs to be less than 2%. All right, so that needs to be less than 2%. Steady state error is defined as the limit as s goes to 0 of s times e over r times r of s. So in this case, if it's a ramp, I put 1 over s squared in there. Okay, that has to be less than 2%, which means it needs to be less than 0.02. All right, now let's think about E of R. Now if I'm talking about steady state means I'm going to low frequencies. Steady state means that frequency is headed to 0. All right, so what I need to do is say, all right, my overall L of S, which is going to be G compensator of S times G of S. All right, at low frequencies, so as omega goes to 0, I know that if the error is going to be anything other than 0, right, clearly that my L of S cannot have another integrator. It already has one. If it had 2 integrators, this steady state error would be 0. Okay? Let's not try to be that aggressive. All right, so let's stick with that one pole at the origin. If that's the case, then no matter how complicated this thing becomes, I can approximate him as 1 over s, right? In other words, this pole at really low frequencies, well below 10 radians per second, he has no effect. Such would be the case for any other pole in 0 that I have. Okay? Now let's assume that the compensator, at the very least, has some gain. Right? Might have poles and zeros as well, but let's at the very least assume it has some gain. Okay? All right, now, what that means is, let's say at very low frequencies, let's plug in what this guy looks like at those very low frequencies, right? So I can say in the limit as s goes to 0 of s times 1 over s squared, so I get a cancellation. E over r is 1 plus 1 over 1 plus L of s, okay? That becomes limit as s goes to 0, I plug in this approximation, so it becomes 1 over s times 1 over 1 plus k over s. That becomes s over s plus k times 1 over s. Those guys cancel. Let s go to 0. This whole thing becomes 1 over k. Okay? So since the steady state error had to be less than 0.02, basically what that says is 1 over k has to be less than 0.02, or k has to be greater than 1 over that. So k would have to be greater than 50. Okay? All right. 1 over k is less than 0.02, so k has to be greater than 50. Okay? So let's go back to here. What that says is, at low frequencies, this whole transfer function would need to become approximated as 50 over omega. Now, this line right here is 1 over omega. So that means I need to take this whole transfer function and lift it up, right? So if I lift this guy up by 50, right? Well, the question is that enough? If I lift it up by 50, right, is that going to be enough to clear this obstacle? It actually won't be, right? Because look at this. Right here at 10 radians per second, I'm at minus 20 dB. If I do a gain of 100, a gain of 100 would get me up to 20 dB at that point. So in other words, a gain of 50 is not going to be enough to clear this obstacle, right? It's enough to meet this error to a ramp spec, but it's not enough to meet this second spec, okay? So instead, what I say is, let's make sure that k is, I'm going to set k equal to 100. So it's greater than 50, and it ensures that I move this point here at minus 20 dB up 40 dB, right? Remember, 20 log 10 100 is equal to 40, right? So I'm going to take this guy at minus 20, and I'm going to raise it up to 20. Minus 20 plus 40 equals 20, right? All right. So thus far, what I've said is that GC of S has to be at least a factor of 100. Okay. Now I'm going to redraw my Bode plot here. Now here's how I'm going to approach this. Here's my obstacle. Okay. At 10, here I am at 100. Here I am at 10 to the third. Okay, so I said I've got this low frequency obstacle I got to worry about, or high frequency obstacle I got to worry about as well. Now, what I'm going to do is I'm going to draw in a couple of key things. I know that for omega less than 10, L of S, let me write it this way, L of j omega, the magnitude of it, is 100 over omega. I also know that from my crossover spec, in order to be able to cross over at 50 radians per second with that much phase margin, I must be falling at minus 20 dB per decade. In other words, the transfer function must act like a single pole at crossover in order to get that much phase margin. That means that for omega around omega C, I need to have this guy acting like 50 over omega, right? Then when omega equals 50, the magnitude of L is equal to 1, okay? And this is acting like it has only one pole, okay? All right, now I can begin to draw in some of these effects on this guy, okay? So let me first draw the different asymptotes. So here's an asymptote. This guy is the low frequency one, okay? He is 100 over omega. Now I know that at crossover, which is, so here's 100. 50 radians per second is roughly about 2/3 of the way between 10 and 100. So it's right there. And I know that at that point, I must also be falling like 20 dB per decade. Now I know also that I have got a pole right here. I have a pole at 10. Back to my original transfer function, I had a pole at 10. So that means that at least for a little while, I had to be falling at 40 dB per decade. What I'm going to do is say, I'm going to try to define a function for this asymptote the same way that I did for this one and for this one. Okay. So what I can say is that in this region, right, this guy is going to be falling at A over omega squared. Right? He's falling like he's under the influence of two poles. Okay? And I have A over omega squared. Now I can figure out what A is because I know that, so in other words, I'm saying this is how I'm approximating the magnitude of L of j omega between 10 radians per second, and apparently I must have a 0 right there at that spot. Why do I know I have a 0? Because I'm going from minus 40 dB per decade down to negative 20 dB per decade. So there must be a 0 at this particular spot. Okay? So essentially, let's call that point omega z. So I know that for omega between 10 and wherever that 0 is, I have the magnitude of L of j omega has to be approximately A over omega squared. Now, how can I figure out what this A is? Well, okay, it's not too bad because I know that at this particular point, at 10 radians per second, it has to have a magnitude of 10. So I can say 10 equals 10, or 10 equals A over 10 squared. Okay. So, right, just plugging in omega equal to 10 in the bottom, setting this whole thing equal to 10, means that A is 10 cubed. Okay? So I know that this asymptote in here has to be 10 cubed over omega squared. All right? So I've got that down. So now I can figure out where the 0 needs to be because I know that at the 0 location, so at omega z equal to omega, this asymptote right here and this asymptote that I have a crossover must meet. So in other words, at that particular frequency, I have 1,000 divided by omega squared is equal to 50 over omega. So if I solve now, I get what? I get omega equals 20 radians per second. So in other words, my zero frequency, my zero must be located at 20 radians per second. Okay, so now what we have to do is we've determined a little bit more about our compensator. What I've determined is that my compensator needs to be at least 100 times S over 20 plus 1. Okay. Now I'm not done yet. All right, so now the overall transfer function would start to look like this. It's falling, then it falls here, then it levels off. Now the thing is, if I stay falling like this, I'm going to miss. If I stay falling as one particular, as just falling off as one pole, I'm going to miss this high frequency obstacle. So I'm going to have to insert another pole, right, to be able to continue to fall off. In other words, here I was falling off in this region. I was falling off at 20 dB per decade. In this region, I'm going to have to fall off at 40 dB per decade. Now, I can determine an asymptote for this guy because I know that this value, negative 20 dB, because I know that at this point, my magnitude has to be less than 0.1, okay? Has to be less than 0.1, and that's 250 radians per second. I can say that here, this guy is going to be A over omega squared, again. And I can say that for high frequencies, I have A over omega squared. And I know that that has to equal 0.1 at omega equal to 250 rads per second. So what do? I say A over 250 squared equals 0.1. That means that A has to be, do the math real quick, 0.1 times 250 squared. A has to be 6,250. Okay? So that means that at high frequencies, this guy is 6,250 over omega squared. Okay? So to figure out where this second pole is located, what I do is I set this asymptote equal to this asymptote. So what I say is at omega p equal to omega, this unknown pole location, I have 6,250 over omega squared equal to 50 over omega. Okay? So I say, what is that going to do? Well, I get omega equals 6,250 divided by 50. So 6,250 divided by 50, I get omega equal to 125 radians per second. Okay, so that point, my GC of S should be decided. I've got 100 times S over 20 plus 1 divided by S over 125 plus 1. Okay, so let's do a check here. Let's plot that whole magnitude. If I look at my L of S, my L of S is GC of S, G of S, which is 100 times S over 20 plus 1 over S times S over 10 plus 1 times S over 125 plus 1. And I can, excuse me, do the Bode plot for that guy. So here's 10. Here's 100. Here's 1,000. There's my obstacles. All right. So if I try to plot this guy, I see that he's going to start here at 40 dB, falling off like negative 20 dB per decade. Then he's going to start to drop until he reaches 20, which is about a third of the way here. Then he's going to level off until he gets to about 125, and then he's going to drop again. So here I'm at minus 40. Here I'm at minus 20. Here I'm at minus 40. All right, and that guy should be able to clear all of the obstacles. Okay. Now what I should check is to make sure this guy actually has the right amount of phase margin. Now how can I do that? Right? Well, I have to check the phase of this guy. Let's check the angle of L of J 50. Okay? Which is supposedly where this guy crossed over. Well, that is, let's do the angle. This guy has an angle of minus 90. This guy here, his angle is plus arctan of 50 over 20. This guy here is plus, or sorry, on the bottom it's minus arctan of 50 over 10 and minus arctan of 50 over 125. So if I go in and evaluate that, that's, so in other words, minus 90 plus the angle of this guy, minus the angle of this guy, minus the angle of this guy. If I go through and do that whole calculation, what do I end up with? I get that this is minus 122.3. All right, so this phase margin is about 57.7 degrees, which is greater than the 55 I specified. All right, so the key thing was really kind of understanding this process of using asymptotes, okay? And in the problem that you guys have, it's very similar, right? The key thing, the thing that's different, right? Remember the hints that I gave you. One is to cancel the pole that is in that thing at 5 radians per second. Cancel it. Make sure that you hit the low frequency obstacle at this corner. And make sure that you hit the high frequency obstacle at this corner. That'll help you to figure out how to do this using the same sort of asymptotic approach.